So each of the four fundamental subspaces is an example of what mathematicians call a vector space. So what is a vector space precisely? Let's say we're working with a collection of vectors called V. So remember, this notation means that V is some collection of vectors in Rn. We call V a vector space if two things happen. The first thing that needs to happen is that the zero vector has to be in the collection. So if the zero vector is not in the collection, we automatically know the collection is not a vector space. The second thing we need to happen is we need every linear combination of vectors in the collection to remain in the collection. Rigorously, this can be stated as C1v1 plus C2v2 belongs to V whenever C1 and C2 are scalars and V1 and V2 are vectors. So if you give me any two vectors in the collection, and I take any linear combination of those two vectors, in order to call the collection a vector space, we must be guaranteed that the linear combination I took is in the collection. So let's look at an example of something that is not a vector space. Here we're defining V to be what's called the upper half space, and this is the collection of all vectors in two dimensions, so all vectors where the coordinates are x and y, such that the second coordinate is non-negative. So here we have a sort of a visual representation of what the upper half space looks like. So let's ask ourselves, is this a vector space? Well, we have one thing going for the upper half space, and that's that the zero vector is there. Certainly 0, 0 has a second coordinate that's not negative, so the zero vector is here. But what about all linear combinations? Well, one thing to note is that the vector -2, 1, for example, is in the upper half space. Again, if you give me a vector with two coordinates, the way I verify whether or not it's in the upper half space is by looking at the second coordinate and asking whether or not it is negative. 1 is certainly not negative, so V, which is -2, 1, is in the collection big V. However, ask yourself, what is a linear combination of just one vector? It's any scalar multiple of this vector. Well, when I scale this vector -2, 1 by the number -1, I produce the vector 2, -1. And 2, -1 has a second coordinate that is negative. So that vector is not in the collection. So here I've plotted -2, 1, which is in big V, and then I've plotted negative that vector, which is not in V. Well, we just took a linear combination of one of the vectors in the collection we're interested in, and we found that that linear combination is not in the collection. This tells us that big V here, the upper half space, is not a vector space. This isn't to say that this collection isn't interesting. Certainly this is a perfectly good collection. It's just not a vector space. Now let's look at something that is a vector space. Here, we're studying the collection big V, which consists of all vectors in R2, such that the second coordinate is -2 times the first coordinate. Well, certainly the zero vector is here, right? Because the zero vector has a second coordinate equal to 0, which is -2 times 0, which is the first coordinate. But what about a linear combination of any two vectors in this collection? So let's say that someone hands us any two vectors, v1 and v2, in big V here. Well, we can look at a linear combination of those two vectors, c1 times the first vector plus c2 times the second vector. And let's take a closer look at what this linear combination would look like. Well, remember, v1 is a vector in this collection, which means that v1 has two coordinates where the second coordinate is twice the first. So I know that I can write this first vector as x1, and then the second coordinate is -2 times x1. And same goes for v2. v2 is a vector in this collection, which means that it is some vector with two coordinates where the second coordinate is -2 times the first coordinate. So v2 has coordinates where maybe the first coordinate is called x2, and the second coordinate is -2 times x2. Now we can take a closer look at this linear combination. We're looking at c1 multiplied by x1 -2x1 plus c2 multiplied by x2 -2x2. And now I can just do all the arithmetic. I can I can do the scalar multiplication with c1, I can do the scalar multiplication with c2, and then I can add everything up. And what do we produce here? We produce a vector with two coordinates, where the first coordinate is c1 x1 plus c2 x2, and the second coordinate is negative 2 c1 x1 minus 2 c2 x2. And what I'm going to do here is I'm going to look at the second coordinate and factor out the negative 2. And now this becomes interesting, because now if we look at what we've done when we've taken our linear combination of v1 and v2, is we've produced a vector with two coordinates, where the first coordinate is c1 x1 plus c2 x2. Let's just call that x. What is the second coordinate? The second coordinate is negative 2 multiplied by c1 x1 plus c2 x2. But this thing in the parentheses here is what we called x, so the second coordinate here is negative 2 times x. So when we take our linear combination of v1 and v2, we produce a new vector whose second coordinate is negative 2 times the first coordinate. This tells us that our generic linear combination of v1 and v2 is in the collection big V. So this tells us that V is a vector space. If we take any linear combination of any two vectors in this collection big V, we are guaranteed by this argument to produce a new vector that also lives in big V. So our previous example was something that wasn't a vector space. Here we have an example of something that is a vector space. So how is this relevant to our discussion of fundamental subspaces? Well, the first answer is we have a theorem that tells us that the null space of any matrix is a vector space. And the proof here isn't terribly inaccessible, so I want to walk through it. The first thing to notice is that the zero vector is certainly in the null space of the matrix, because if you want to test whether or not a vector is in the null space, multiply by A and check whether or not you get 0. Well, since A times the zero vector is the zero vector, we know that the zero vector is in the null space. What about a generic linear combination of any two vectors that start in the null space? So what happens if you give me v1 and v2 that live in the null space of a matrix? Well, I'm going to now take a linear combination of those two vectors and verify whether or not that linear combination is in the null space of our matrix. The way we check whether or not something is in the null space is we multiply by A and we verify whether or not we get 0. So I'm going to take A and I'm going to multiply by c1 v1 plus c2 v2. And the first thing to recognize is that we can distribute A across this linear combination. This gives us c1 times A v1 plus c2 times A v2. And the thing to notice here is that v1 started out in the null space. So what happens when I take A and multiply by v1? That should give me the zero vector. What about v2? Well, v2 is also in the null space. So A times v2 individually is also equal to 0. So now I know, after distributing my A, that what I'm really looking at is c1 times the zero vector plus c2 times the zero vector, which is really just the zero vector plus the zero vector, which equals the zero vector. So this argument tells me that if I start with any two vectors in the null space, and then I take a linear combination and multiply by A, I produce the zero vector. This tells us that the linear combination we were looking at does live in the null space. So if you start with any two vectors in the null space and you take a linear combination, you produce something that lives in the null space. And this is the proof that the null space of any matrix is a vector space. What about column spaces? We also have a theorem that tells us that the column space of any matrix is a vector space. How does the argument here work? Well, let's say we start out with any two vectors in the column space of a matrix. Well, let's now look at a linear combination of those two vectors. Well, the first thing to know is that, well, if v1 is in the column space, what that means is that v1 is a linear combination of the columns of A, which means v1 is equal to A multiplied by some vector, which I'll call x1 here. Same goes for v2. Since v2 starts out in the column space, I know that it is equal to a linear combination of the columns of A, which means that v2 is equal to A multiplied by another vector, which I'm calling x2. So now I can make those substitutions in my linear combination. C1 times V1 plus C2 times V2 is the same thing as C1 times AX1 plus C2 times AX2. And now, of course, I can factor out A from this expression to obtain A multiplied by C1x1 plus C2x2. And think about what this is saying. What this is saying is that if we start out with any two vectors in the column space, we've just laid out an argument that any linear combination is equal to A multiplied by some vector. And that's exactly what it means to live in the column space of a matrix. So our linear combination, by this argument, must also be in the column space. Also, we know that the zero vector is in the column space because the zero vector is equal to A multiplied by the zero vector. So linear combinations of any vectors in the column space always remain in the column space, and the zero vector is in the column space, which means that the column space is a vector space. So the way we've been presenting it, null spaces and column spaces have different definitions, but there is a theory that unifies these concepts, and that theory is called the theory of vector spaces. So what we'll start to do now is we'll start to study vector spaces in greater depth.